Thank you for the introduction, and also many thanks for the invitation, for the opportunity to give a talk to you guys over here. So, as you just said, I'm Yarin Gal. I'm an associate professor of machine learning, or AI, as the media calls it, at the University of Oxford. We're going to talk about the art of AI extrapolation. I'm also going to say that I'm it's been a long day, so do forgive me if the talk becomes a bit less coherent at times. Let's start with this very simple painting, which is a very famous one. So who recognizes this? What is this painting? Starry Night. Well, actually, that's not Starry Night. This is Starry Night. This is a pretty nice example of what extrapolation is. So this is a case where we took an object, in this case a painting, and we tried to extend it beyond the canvas, beyond the frame of the painting. You can do that with paintings, for example, taking canvas, trying to see what it would look like outside of the frame. You can do that with sequences, time series, for example. You can do that with sentences, sequences of words. Basically, trying to see what could be, when we try to extend the painting or the sequence of the object, what could be beyond the boundaries, beyond the frame of the object. So I'm going to try to give you some intuition into what's going on, or what does it mean? What does it mean to extrapolate an object? In this case, extrapolate a painting. Over here, I took the original painting, and basically I'm just going to put it on a grid. So we have a 500 by 500 grid, and each location in the grid, each point in the grid corresponds to a location in the painting. What I'm going to do next is I'm going to start rotating the grid very, very slowly. Basically, it's basically the same as I'm taking the painting, just putting that on the floor. So it's the same as putting the painting on the floor in your flat. And then I'm going to do something very interesting. I'm going to start deforming the painting. I'm going to start pulling, I'm going to start pushing and pulling, stretching stuff out of the painting. I'm going to start stretching the canvas to get all the light parts, the bright parts, I'm going to pull them towards me. The dark parts, I'm going to push them away from me. And very slowly, we're going to see some very interesting patterns emerging over here. So you can see, for example, the stars are very, very bright. They basically get pulled a lot towards us, get stretched a lot. The tree is very dark. It gets stretched much less. You can see over here, it's very nice. The moon itself is actually darker than the light around it. So the moon basically sits inside the dip, surrounded by the light, generated by the moon. We can take this thing, we can take this deformed, stretched painting, and then we're going to look at the boundaries. We're going to look at the boundaries of this painting. And specifically, we're going to look at the line over here. So this is basically defines a function. If you take all the lines on, all the points on the line over here, then you can see that this function basically goes up and down and up and down and up and down, and then you can use this thing in order to try to extend the painting. The naive thing that we can try to do is basically just copy the same thing again and again and just see what it looks like. So we're just going to copy that. And we're going to basically take the same pattern of stretching up and down and just extend that outwards. And we're going to get one possible extrapolation. That basically, if we now look from above at that painting, it's going to look like that, which doesn't look too convincing. That's one possible extrapolation, extension of the painting beyond the frame. Let's look at another one. So we're going to take the painting again. We're going to put it on the grid. We're going to start rotating the grid very, very slowly. Basically, we put the painting on the floor again. We're going to start stretching the painting. We're going to start pulling towards us all the bright parts, pushing away from us all the dark parts. We do that very slowly. Basically, we get all these nice patterns. We're going to look at the boundary again. But now, instead of just looking at that single line, we're going to look a bit more inside the painting. Basically, what you're going to see is that inside the painting, we have lots of interesting patterns over here. If we actually look at the pattern within the painting itself, we can see it's actually high, and then it goes low over here. And over here, it goes slightly lower and then even lower. Over here, it starts low and then it goes slightly high. And we can use that information to decide how to extrapolate, how to extend the painting outwards And then using that information, we can actually get much more interesting possible extrapolations. And then we can rotate that back to see what it looks like. So that gives us another possible extrapolation, which looks much nicer, isn't it? By just looking at the patterns inside the painting itself. I'm happy to share with you some other works of extrapolated art that we've done over the years. So this is Starry Night over the Rhone by Van Gogh as well. That's the extrapolation. This is The Sower by Van Gogh. And the extrapolation. The Great Wave by Kanagawa. So this was actually on display in the British Museum. I'm not sure if it's still on display in the British Museum now. And the extrapolation. And lastly, this is From the Lake by O'Keeffe. And the extrapolation. We have some new pieces as well. So just like making this talk, just building the visualization tools to show you at the beginning, basically started looking at how can we visualize these things for extrapolation. So I did the same thing of stretching the painting out of the frame, out of the canvas. But instead of stretching like what looked at before, basically now I'm stretching each individual brush stroke. So you can see, basically this is Van Gogh's Starry Night in 3D. You can zoom in and you can zoom in a bit more and you can see the stars, and each individual brushstroke is basically pulled towards the viewer, towards you. You can see like how the stars themselves basically have this interesting fractal-like shape. And actually a student of mine, Aidan Gomez, has some his own artworks as well. So this is using a very different technique. This is not using extrapolation, it's using other techniques in machine learning. This was on display in an art exhibition in Oxford recently. We have basically we're building an art school within our machine learning group, which actually is a good opportunity to segue to the way that we actually apply these sort of things. How do we use the same tools that we talked about for machine learning, so for art, how do we use these things for science as well? So let's go back to what we started from. So we started from Starry Night. And then we looked at the possible extrapolation of Starry Night. But who said that we had, like, we didn't actually know what we had outside of the painting. We don't actually know what the town looked like from just looking at this painting itself. We don't know that we had more buildings over here. We don't know that we had more buildings over here. It could be, instead of having buildings, we actually had some more bushes over here. This is another possible extrapolation. All of these are equally valid possible ways of extending what could have been. And we actually use the same exact techniques in science. So this is an example in climate science where we build climate models. So over here, we have the CO2 levels, CO2 concentration at Mauna Loa, Hawaii over the past 40 years. And we want to know what the CO2 level will be in 40 years' time. For example, we use these sort of things to build climate models. We have one possible extrapolation. Over here, instead of having a painting, we have a sequence. We take the sequence and repeat the same patterns in the sequence. And we say, oh, we think the CO2 level will be here. But like with art, we can also have other possible extrapolations. We can have this extrapolation. We can have this one as well. Each one of these is actually a plausible extrapolation. And in science, we actually use all of these. We try to generate all the possible extrapolations that we can have, looking at how likely each one is. Some of them are more likely, some of them are less likely. And when we build climate models, we basically try to take into account all the possible likely extrapolations, all the possible likely extensions that we might have for these sequences. So this is a field, like the field in which we generate these multiple extrapolations, multiple explanations of what could be in the future is called probabilistic modeling, Bayesian probabilistic modeling. We actually use the same AI tools. Actually, I think it's quite beautiful that we use the same AI tools for art as well as for science. So the same tools that we use for extrapolation, we use for the climate models we talked about. We use these same tools for autonomous driving. So in the next couple of years, we're going to start seeing autonomous cars on the streets of London and everywhere around you. And all of these different cars basically use the same sort of tools that we talked about today. A car, in this case, would look at you as a pedestrian, would see you walking in front of it, and would try to predict, would try to extrapolate where you will be in 5 seconds' time, in 10 seconds' time. Will you be over here? Will you be over here? And based on that, it tries to decide which direction it should steer. We have the same thing again in robotics, where we use this sort of extrapolation, use these sort of machine learning tools in order to teach robotics how to act in the world by themselves. So for example, Amazon is using these sort of things in order to build like gripping hands that can basically take an item and put it in a basket. We use some sort of things in medical applications as well. So in healthcare and medical applications, where we take medical records and we use these to diagnose whether a patient, for example, has melanoma or whether they have diabetic retinopathy or not. And we have the same sort of extrapolation looking very similar to this sort of thing over here. And we even use these sort of tools in astronomy. So we use these sort of tools you give me an optical image of a galaxy, and I need to say whether it's a simple galaxy or a featured galaxy, smooth or featured galaxy. And we use sort of tools in order to basically build these catalogs, sky catalogs that we use in sciences. I really hope that this talk inspired you to learn more about machine learning. Whether you want to use it for art, in which case, you're welcome to go on this website and get some more inspiration about what we can do with machine learning for art. Or please go on the group website for our group in Oxford to see how we use these sort of tools for all these different scientific applications that I mentioned. Thank you so much.
If anyone has any questions, please raise your hand and I'll come and get you a microphone.
Would you consider any of these examples over there on the screen AI? Because surely if they were AI, would they be self-developing?
So AI has become a very ambiguous term. What you see in the news as AI is machine learning, because it often happens that people just in the media and the news start using the term AI to talk about these sort of things. AI in the literature, in science fiction, is the sort of thing that you imagine as like something that becomes sentient and trying to take over the world. That's not the stuff we're talking about over here.
Okay, thank you.
I'm just curious when you mentioned the different possibilities of extension. Is there like a limited number of possibilities which are regarded as the most probable scenarios, or is there actually a limited number? And also, to what extent do you need to have human supervision to check what are the most likely scenario?
That's actually a very interesting question, because if I ask you, let's look at these example for the paintings. So like the first extrapolation that we had in the first slide, that's many, many slides ago. Here. Do you think that's a good extrapolation? No. What makes that a bad extrapolation and the other one a good extrapolation? Well, one possible answer would be your personal taste, that you think the other one is prettier than this one. Another possible explanation is that the other one follows actually a different distribution. Or we can say that the other one is more likely to, like you would expect to see the other one because it seems more similar to what you expect towns to look like than what we have over here. So that is actually what we develop. We develop these sort of tools to build possible extrapolations, possible extensions of paintings or like sequences of CO2 levels in Honolulu, Hawaii, that can tell us, not just give us an extrapolation, but also tell us how likely they are. Basically tell us, this is a possible extrapolation, but it's very, very much unlikely. The other one is also possible, but is much more likely. And if you look at the two examples that we had with the bushes compared to like with the buildings, then you can say, well, actually, I think both of them are equally likely. So it's basically part of the methodology that we develop, that we want to decide which one is more likely and which one is less likely.
So in this one, is the extrapolation predicted by looking at what already is there and just duplicating it?
Um,
Because I see that
broadly
house.
speaking, yes. So broadly speaking, yes. So the simplest way of doing extrapolation is look at the patterns that you already had and repeat them. That's actually the same as what we did in the CO2 level. Like when we look at CO2 levels, we look at the patterns. We have periodicity, which is basically every month. So we actually have 12 like up and down each year over here. So that is every year, and then within that we actually have even find a pattern. And then we just look at these patterns and use these to extend in this case, the sequence, in this case, the painting. And you can say that we have a house over here, therefore it's possible that we also have houses over here. But you can also it's possible that we have houses over here that look slightly different, not necessarily exactly the same.
Because, yeah, this one doesn't look as natural as it would. How far could you stretch it?
Infinity. It might start looking the same at some point. It will not, it will just repeat the same house again and again.
Can you use this to track diseases spreading throughout the body in a medical point of view?
People are. So people are using these sort of tools, not exactly what we talked about, but people are using these sort of tools to diagnose and to track diseases, both within the body and also how they spread within the population.
In the wave one, how did you predict there were going to be more waves? Because there could have just been less waves.
It could have been less waves, actually. So that's the same example over here. We can have more bushes or we can have more buildings, and we could have equally been less waves instead of having more waves. Could have been more waves over here and less waves on the left-hand side. Yeah.
A couple more questions if anyone would like to ask anything else.
How much can you trust AI to start extrapolating graphs? Because how different is it to normal extrapolation?
Well, actually, I think that is exactly why we want to have things. So this is exactly why, if you ask me what the CO2 level would be in 2040, I don't want to tell you, oh, it's going to be this thing over here, because it could also be this thing over here and could also be this thing over here. So in a sense of trust in AI or in these machine learning tools, I would actually want my tool to be able to tell me that it could be any one of these things and how likely each one of these things could be. And based on which one is more likely and which one is less likely, I can build a model that will take all of these things into account. And that basically allows us to build these sort of safe AI tools. Cool. Thank you very much.
Thank you everyone for coming. Just to say, this talk is part of a series of lightning lectures taking place throughout the day, so do check out your programme for other talks going on. Enjoy the exhibition.